afternoon. So today's our presentation is gonna be common mistakes that happens in a transfer learning-based project in computer vision. So here are our contents. We're gonna see very in a short recap what is transfer learning is specific to the computer vision. And we will see some live demos performed by Ronald. And we will see the mistake associated there. And to overcome some problem, we switch to data augmentation, which is an important technique to deal with the small data. There also we will see some mistakes, and we overcome them. And at the end, we will see some model explainability. So let's get started. What is transfer learning? Transfer learning is a way to use a pre-trained network trained on a large image data set, which contains millions of images with 1,000 image categories, which is ImageNet data set. And it's a way to use that into your custom problem. Well, all these big pre-trained models are readily available in all the high-level deep learning frameworks, such as FastAI and Keras. And we will use FastAI for their demo purpose. And here are some list of large pre-trained models. And we will use specifically ResNet 50 for the demo. And so why we need transfer learning? Well, it offers very important advantages, such as it allows to work with a small data set. It provides a higher accuracy because since already the good weights parameters are already learned over the huge amount of images, so it's very generalized. And it also leads us to do a fast model training. And we will see that it's very fast using in just Google Colab. We can do it in some minutes. Yeah, so we don't need to train the whole model. We just train only the customized layer which we're going to put it. And this is the ImageNet dataset which we're going to use for the pre-trained models. And it contains, as I mentioned, millions of images with over 1,000 category or classes, which contains, for example, buildings, people, etc. So in computer vision, there are two kinds of transfer learning. One is a feature extraction, and another is fine-tuning. Feature extraction means that we literally want to use our pre-trained model as a feature extractor. So what we're going to do here, we use the whole model, remove the last customized classifier, and we add up our own customized layer, customized classifier there, and we freeze the main convolutional base. So we don't train these weights, so because they are already learned. And we just put the images, take out the features from there, and use it to our custom classifier, which can be any machine learning-based classifier, for example, from logistic regression to softmax to even decision trees or random forest. And in a very similar setup, we use fine-tuning. But here, we really tune the part of the main convolutional base. So for example, it's very typical to use the last layers, which is closer to the output classifier, closer to that. And we just fine-tune that. And we jointly train our custom classifier, and which we usually use the softmax because we do the end-to-end training there. And we also just let the updates of the weights until this last layer of the last convolutional block of our main pre-trained model. Now, since we have seen two kinds of transfer learning in computer vision with context with deep learning, so which one to use? Well, it depends upon two important parameters. So first is what is your size of the database, is either small or large, and the similarity of the database with respect to the pre-trained model database. So for example, if you have a large data set, and it's similar to the pre-trained model one, then you would like to go to fine-tuning, because you just want to adjust the last layers of the main convolutional block, and so that it adapts to your custom classes that you want to do the prediction on. And the second strategy is if you have a large data set, but it's very different from the pre-trained models data set, which is usually we use ImageNet, then it makes sense actually to use to train the whole model since you have already large data set. And important to note here, you can already use these large networks. You use them as a initialized weights, and then you update them. While in the third strategy, if you have a small data set, and it's similar to the pre-trained data set, pre-trained models data set, then you would like to do feature extraction because you just use the pre-trained model as your feature extractor there. And lastly, if you have a small data set and it's different from the pre-trained model's data set, then you will like to use only the upper layers of the convolutional block because they learn to detect the low-level features, for example, edges, contours, colors, etc. So now, we have seen the 4 strategy. To just conclude it, to give a very practical example. So for example, if your task is to classify different kind of animals images in a zoo, then use any model, pre-trained model, which is trained on an ImageNet data set, because it has seen already all the images of a living creature. So it contains, the images are there. So it can generalize well. However, if your task is to classify, for example, cancer versus non-cancer cells, then ImageNet should not be used since it does not see the cancer cells there, and the domains are different. So this is how we decide the transfer learning. Now, OK, so enough of transfer learning. We do a practical session. Oops, sorry. Let's classify dogs and cats. It's a classic demo. Ron.
So we will be training in the Google Collaborative, which is a really good way to test some of your ideas at first. Do not use it in your company, as though Google has access to all of the things you are using there, and in the terms of conditions, they can use all the code that you write there. But it's super good and for free for just the first testing. After overloading the memory, you get actually to the P100 graphics card, which is a decent graphics card to be just in your hands, in your laptop, provided for free. So to load the data set, I've created 3 data sets by just scraping the first images that appear in Google image search. And then I removed some of the really, the most non-correct images that were there. We use the data through the loading capability of FastAI. FastAI is a great framework for the first try of different ideas that you have. If you go to production, I would suggest, and we do it in our company, to use Keras on top of TensorFlow, for example, or even go with TensorFlow as a whole. We just load the images, normalize them to one size that's needed for the training using these convolutional networks. And once the images are loaded, we can start working on them. The data set is super small. That's the reason why we are using transfer learning. As you can see, we have only 363 images for the training and 90 images for validation. And for the test set, we are using 463 images. To load the model, we just use a pre-trained model from the FastAI, or rather from PyTorch. That's pre-trained on the ImageNet. And then we train it using the fit1 cycle policy, which is a new default way for FastAI to train neural networks. It's super efficient, but it's out of the scope of this presentation. So if you want to go deeper why this works, please search it on your own and read the full paper. After loading the model, we can see the first and last layers concatenated of the model with all the layers inside of it. And then we can start training using this one cycle policy. Because the ResNet was already pre-trained probably in a few days on several millions of images, we are now training only 500 images. I can get my whole training done in literally 13 seconds here in the browser, or rather on the server. So you can see that the accuracy is 100%. There is something really fishy about that, even though cats and dogs are already in the data set itself. So we should always, especially with transfer learning on a really small training image data set, we should evaluate it a bit further. That's why we have our own evaluation, which first calculates the accuracy that was calculated before on the validation and on the test data set, but also we print out the confusion metrics, so we have a deeper understanding of the results. The generation of this, as you can see, 100% accuracy, isn't that just great? On the test set, it should be a bit lower, because the first images were used, the validation, to specialize on the best validation loss based on those images. That's why it's super important to use test data set. People do not do that in practice for some reason. And as you can see, even though we would say that our model has 100% accuracy, it actually will be closer to 88% in practice once the model is deployed. Also see that the data set used for testing is as big, or in this case even bigger, than the data set used for training. That's super important with such a small training data set. But can this result be further improved? Is there a way to do even more with such a small data set, not even having 1,000 images?
Okay. So, well, we have seen like 88% accuracy in the test data set is reasonably good, but it's not good for the production. So we don't want to put that into the production. And one problem was there, it's because of the too little data. And it causes the model to do an overfitting problem, which is a very big problem in general when you train neural networks, because they are very highly prone to overfit very easily. So what we need more data, of course. But it's not only sufficient more data. What we need is actually more variance in the data. So we need more variability that we can show to the network. And as we already know that in a practical situation or a scenario, it's hard to get all this data in a real world. So what we're going to do, we're going to apply a technique called data augmentation. And it's an important technique which allows us to generate samples out of your given training data set by applying different kind of geometric transformations onto your existing data, and it generates more images for that. And it's also, from this, since we can generate more data, and we try to then solve this overfitting problem. So hopefully we will get more accuracy. And these are some examples of, for example, you have a range of a random vertical shifting of an image, and you can create 6 images out of it. So it's just a parrot image, and I applied random range of a vertical shift. I get 6 data samples. Similarly, I apply different range of brightness. I get from low, dark to high to brighter image. And similarly for the zooming. And there are a lot of different techniques which are available easily to use in fast AI and Keras. OK, so now let's apply data augmentation to our current problem, and let's see if we improve the accuracy, test accuracy.
So as you can see, I'm using the transformations that are directly in fast AI. That's why it's super easy and fast to prototype with fast AI. I just put in some flipping, rotation, lighting, zoom, warping, all the things that are there out of the box. And if I train the model using those transformations, I should see probably worse results on the validation set, but at least the validation and the results on the final testing should be way closer to each other. So it's not 100% to 84%. That's a bit too low for using such a powerful model as is ResNet, trained on ImageNet, especially because ResNet already contains images of cats, dogs, and those classes, even of special breeds of cats and dogs. And if we go, the accuracy of the testing set is just awful, 61%. It's almost like flipping a coin. So what could be the problem here? Let's look at the images that are inside there. Okay, that's a bit much. Yeah, we overshot the augmentation. The important thing with augmentation is that the way we augment the data still has some some logical meaning in the terms of the data set we are using. So for example, if you are training a text classification, let's say it's not almost solved, but Git pullable, then it's a good idea to do rotation of the text in our training data set because we want to be able to classify the text in any rotation. What is not a good idea is to do a flipping because, well, the text doesn't look that way if we are reading it. So we should really always think about the transformations if they make sense, because we are basically providing extra information by thinking about what are the possible transformations that may be met in the real world afterwards when we do the inference of the model. So let's now fix the data transformations. So we rotate, we don't flip the cats and dogs, so they are not like flying legs up, even though it may make sense. We rotate it a bit less. We change the lighting, and the main thing, we change the maximal zoom to only 10%, and also we do way smaller cutouts than we did before, so we do not cut out basically the whole image. Let's see if this actually helps. Let's not do multiple cycles, so it's quicker to train. Okay, we look at the images. So now it's more reasonable. Maybe some fiddling with the augmentation would be needed to achieve better accuracy. All of the examples here are super exaggerated so that we get our points done within 14 seconds of training. So please keep that in mind. And if we look at the training cursor, 98%, that's reasonable for such a task. Accuracy on the test set should be higher than 61% now. Like this result, here we again touch of having such a small validation set, that like losing almost 2% is just not classifying one example. So those are just inherent problems with having such a small data set that's smaller than 1,000 images. And we see that the test accuracy is 83%, which is for such a small data set and just random data augmentations, pretty decent result.
Okay, just to summarize it, so what we have seen, applying data augmentations really helps in coping with this small data problem, but you have to be very careful. We always should see the output images, because sometimes this transformation can add distortions in your images which are not desirable. So I give you a very quick example. So for example, if your task is to classify or quantify an image quality, so you want to classify basically blurry image versus non-blurry image, so you have to be careful to not apply also interpolation which brings to your positive class, so for example, which should be non-blurry and a blurriness there. So it can really flip the situation. So you have to always see the augmentation results and decide on that which transformations you actually need to apply. And now the question arises, so we have seen transfer learning and data augmentation with carefully selecting the parameters of the transformation. So does it solve always all the problem? So we have created somehow a kind of a pipeline. Let's validate this pipeline to another data set. So to classify web UI elements, which are like buttons and tabs, something like that. And let's see, Ron.
So do we have AutoML for images? Do we have no-code AI now? Let's see on the UI elements. So we are using the very same thing of having pre-trained ResNet 50 model or architecture on the ImageNet dataset. Now here you can see some random web scrape of images, of inputs, images with buttons, and some icons. Now if we do the training on this and validation, we can already see that the validation accuracy is lower, but like that's to be expected because we are classifying three classes instead of 2, even though it shouldn't be so much lower. But then for the test set, the results are completely off. Like for free classes, yeah, 58%, one should say. It's like almost twice as good as flipping a coin. But this is not a production-grade model, and please do not use models with 58% accuracy in production. So the transformations look pretty like okay. They are not completely off. So what's the problem here, Sanchit? Why this model is underperforming?
Okay, so as we remember, we have said before, like during the transfer learning, you should always check if your pre-trained model's data set contains the images of your task which you are performing. So for example, we wanted to classify web UI, but we use ResNet 50 model which is trained on ImageNet dataset, and it does not contain any images for this web UI. So what has happened? Just the image domains were different, and it underperformed our results. And yeah, this is an example. So ImageNet is not similar to the web UI elements. OK, so we have another demo. Let's classify hot dogs, because this is the most interesting thing.
Yeah, apparently, I've read somewhere that just classifying hot dogs is enough for successful startup these days. So at least to go to B series, right? So let's do a small proof of concept of classifying hot dogs. So let's load our data set and look at it. So we have two main categories, hot dogs and not a hot dogs. As the main contestant of not a hot dog for this data set is, as you will see soon, is pizza, because pizza is the greatest enemy of hot dogs. Because one should argue that it's basically hot dog with just different shape from Italy. But let's see what do neural networks think of this and if they can classify. Actually, do you think that using, again, ResNet 50 trained on ImageNet is a decent idea for classifying hot dogs? Yes, it's a great idea because there are literally categories of hot dogs and pizzas and other food in the ImageNet dataset. So we basically checked all of the things that we done correctly before in this presentation. So let's see what will be the accuracy. I'm spoiling it a bit. Sorry for that. But if we train only using one cycle, again, this is not exactly equal to one epoch. The one cycle policy means that you are starting with a low learning rate, then you slowly increase it and then decrease it over even several epochs. So the training accuracy is 93%, which could be for sure improved given better data set. But 5 images wrong out of the validation set, that's reasonable. Let's see for the results on the test data set. Let's say we would like to achieve 90, 92+% accuracy for the production. So when we are showing it to our investors for the first time, we have only 8% chance of not getting the funding. Oh, it's under 80%. We are not getting the funding, right? And especially not because many not hot dogs are classified as hot dogs. So we want to investigate it, right? Like confusion metrics has just so much it can do for us. So the thing we can do is we can look into the activations of the neural network, and not only to the activations, but there is a really good paper about GradCam,
Gradient classification
from 2017, which is a way to see which pixels in the image are basically the most corresponding for the decision made by the model. So for that, this is also for free in the Fast AI, just for 2 lines of code. We again instantiate the interpretation classifier, and then we do the plot top losses function on it. And first we show random 4 images, even those that were classified correctly, and show the heat maps for them of the activation that led to the decision of the network. And then we show the 4 images that had the highest uncertainty or that were the most likely to be the other image based on the prediction of the network. So if you look at that, first we have the images that are actually hot dogs, and they were classified as hot dogs. You can see that it's 100% sure, the network, that those are hot dogs. And the activation looks decent, right? It's looking at the sausage, right? And not around it much. That looks good to me. But then if we look into the other images that had the lowest probability of being the correct class, we can see that the model is a bit like confused where to actually look, right? It's like looking to corners and everything. And if you look into the images, like like this image for sure is not a hot dog, but our data set had mostly pizzas as not the hot dogs and not the ingredients for pizzas. But this is only the validation set. If we now look on the training set and the results of that, we can again see that for the images that were clearly a hot dog, it learned pretty well if you have hot dog in the sky, even though I made sure that there is no hot dog in the sky in the training or validation data set. It only looks at the hot dog and not on the sky or anything like that. And the same thing for the other hot dogs. But then if we look at the worst cases, you see that those images have pretty much zero activation. And then you should look for those instances. There are basically many things that you can explore using this technique. In this instance, I see that all of the images are drawn, and especially this is like definitely hot dog for people, but not a hot dog for a neural network, because especially convolutional neural networks like ResNet50 are really looking at the texture of the image and are basically absolutely disregarding the shape of the image. There are special techniques to force the network to look at the shape and not on the texture of the image, but pre-trained models like this, ResNet50, is really looking at the texture of the image. And as you could say, the texture of a drawn image is way different than a texture of an actual hot dog. So that's why we have zero activation. The other thing that's not shown here, but that can also happen, is that you will see that the network actually overtrained or something completely else than you wanted it to. Like there is the really famous data set of lung cancer, where actually there was like a really slime shadow of a ruler being put to every single image of a patient with lung cancer. And then the network basically mainly trained to see if there is a shadow of a ruler in the image or not, which is worthless for inference, because in inference you either do not put the ruler to any patient or to all patients. And the last thing that we can try is just unfreeze the model, right? Like that's one thing that we said in the beginning that we can do, and see if the results will just not get better if we train it on the 400 images using unfrozen model. Again, 14 seconds to train. Really nice. Okay, so the accuracy got even lower. You can see that it really, the model really tries to predict not a hot dogs instead of hot dogs. And that's mainly because not the hot dogs are all kinds of things, and hot dogs are really specifically the hot dogs. And hopefully there will be the heat map soon. Oh yeah, accuracy 50% for 96 on binary classification. Here you can see that the model is totally degenerated. And if you look at the heat map, yeah, it just doesn't know what to look for. So that's it for the actual coding. There will be a link in the presentation. You can use this code with your own classes, with whatever, and start training. I encourage you to try Fast AI for the first proofs of concept. The Google Colab is really cool, especially now. You get for free to try the TPUs from Google, and with TensorFlow 2, they should work out of the box, hopefully, they claimed. And I give it to Sanchit.
Okay, just to summarize, we have seen a very important technique that class activation map. So it's very important when you are done with the training of the model. It's not finished yet. So you should really check it out, the class activation map, to really see if your model is learning the background or the object of interest. And so this kind of techniques enables us to see which part of the input image is really contributing for the decision process of the trained model. So this is our recommendation. So as a summary of what we have seen a quick overview about the transfer learning, different kind of, and why we use transfer learning, and how to decide. And then we saw an example where, because of too little data, we could not achieve a reasonable accuracy, so we used data augmentation to overcome this problem. However, what it leads, when we don't see the augmented images, it leads to it harms our model accuracy. And then it's not only enough using transfer learning and data augmentation if your model, if your domains are different of your task and of what the pre-trained model data said. And lastly, we see class activation map, which is a very powerful debugging tool, which allows us to visualize what the model is looking at into your images. So this is explain the model's explainability. And yeah, and as Ron mentioned, code is available for free. You can check it out. So because of the timing, we have not covered a lot of important other topics, as Ron mentioned, but we have used already in our code. So first thing is the cyclic learning rate, which is highly encouraged to check it out. And other other techniques to overcome with the overfitting problem, we have not seen yet, but we have mostly used it. And that's it. And this is our company, Scalable. So we are an IT company, and we have nearly all the departments. So from AI to web development to backend to front end, and also to mobile development. And that's it for our talk. Thank you very much for your patience.
Questions? Questions now.
Oh, yeah.
Thank you, Ronald. Thank you, Sanchit. So can we switch to the Slido channel? So just in case you guys have forgotten, slido.com #WAD2019. So when you go in there, you can also upvote the questions that you would like us to address. So please do that, even if you don't have your own questions. Let's look at the first one. In a transfer learning setup, how do you choose the best base model?
Well, I think it's usually you choose the one which is latestly released because it always shows a higher accuracy. And especially we encourage to use, like, if you don't know anything, you should go with a ResNet because it's a good model.
It's a good baseline, and then you should look for special characteristics on your learning setup. So for example, if you have a huge variety in the size of the classified objects, you should go for a Trident net, which is like architecture, I think 1 year old, that like somehow solves those problems of different sizes. So you should think about what's special about your data set. Always use the ResNet 50 or higher as the baseline, but then also look for the special properties of your data set and try to search for some research that's addressing those specialties.
Perfect. Okay, next one. ImageNet and Cocoa are not really open for commercial use, and hence they're pre-trained models for transfer learning. How do you handle that in the industry?
Well, the good part is at least the pre-trained models are available for free, and you should look at the licenses, and most of them are open licenses, so you can really use them for your industrial setup.
Okay. So the next one, what's the paper that you guys mentioned? What's the paper that we can look up on the faster learning mentioned in the beginning? Thanks.
It's called Gradient. No. This was a cyclic learning rate paper, I guess.
Yeah. If you look into the documentation on fit one cycle in Fast AI, they have directed the link to the paper, and you can explore it there.
Okay. So the next one up, does transfer learning get useless or get limited starting from a specific amount of data?
Well, kind of, yes. If you have a really too less data, then it's probably better to use a very simple network. Then I would not go with the transfer learning. Otherwise, if you have a decent amount of images, for example, about 500 to 1,000 number of images, then transfer learning is definitely way to go.
Okay. So the next question, can the first few layers be trained or some pre-processing done so the network is invariant to transformation of the images instead of generating more data?
Okay.
Is that clear?
Not well, okay, I think I didn't get it. You get it?
Yeah.
Well, in general, it's always good to use more data. I mean, that's a baseline. More data will cope up with your overfitting problem. I mean, that's a rule of thumb.
Exactly. Who posted
I
this
don't know.
question?
I think I understand now. Is it if you mean like that you should use a network that has the same result independent of the transformation done on the images? Like you are already using that, doing that using convolutional neural networks. Like if any one of you tried, for example, doing the MNIST with a dense network instead of convolutional network, there you can see like by moving to the convolutional networks, you are basically using this, right? Because in convolutional networks, it's almost invariant where the object is in your image. And like, it's not invariant to the rotation, for example, but there is really interesting research being done by the creator of convolutional neural networks. They are called
Jeffrey Hinton?
Yes, but capsule networks, and the main thing about capsule networks is that he's trying to address those problems, that you have capsules that specialize to extract some properties of the images. So go this way, but it's still ongoing research. So for now, just do the transformations. Data augmentation is pretty cheap compared to the actual training of the model. Perfect.
Okay. Next question, hot dog or not hot dog? Perfect. Anyway, so how about all these YOLO, SSD, RCN, hot dog versus non-hot dog task? What's your opinion? What's the best?
Well, it's first thing, what we have presented here was an image classification task. And what is in the question is mentioned is an object detection task. So it's like you are detecting where is the hot dog in your image. So I think I correct a bit this question. So it's not about classifying. So these techniques are not about classifying hot dog versus non-hot dog, but they are object detectors. So they are like given an image, you find the bounding box, basically a rectangle, which encapsulate where is the hot dog present in that image. And on the top, of course, YOLO, SSD, and well, you don't go with RCNN because it's kind of outdated. So maybe the better version of it is faster RCNN, but it's very computationally very heavy. But in my personal opinion, I would go with SSD, then the YOLO first version, and because there is a 3 version also in addition to YOLO. So either I will go to YOLO version 3 or SSD.
I would prefer MobileNet version 2 and put it on some accelerated hardware and put it on Raspberry Pi 4, which is really powerful. Try Raspberry Pi 4. Put the accelerated card into it, and you can get 100 FPS of MobileNet 2, and that has really good accuracy.
And just to mention, in addition, all these object detection techniques, so YOLO, SSD, RCNN, they all use transfer learning. So they all use pre-trained models, like as a backbone.
Yeah.
Okay. The next question. So how would you know if you're improving a pre-trained model or making it worse?
Well, if you're using a pre-trained model, so as we mentioned about the strategy, you have to choose. So usually you don't touch the pre-trained model, usually. So depending upon feature extraction or fine-tuning. So if you are doing the feature extraction, then you freeze them. So freezing means you don't allow weight updation during the backpropagation. And while in the fine-tuning, you just adjust the lowest block or the layer to fine-tune to your custom problem. So I would say that you only have to check it out, the custom layer, what you are putting in front of the main convolutional block of the pre-trained model.
Yeah, if you have little data, you saw at the very end of the code that if you unfreeze the model I unfroze the whole model, then it will just get worse because you have so little images that it will just mess up the convolutions down the line. So just use frozen models until you have several hundreds of thousands images at least.
Okay. Why did you not recommend using dropouts?
Okay, so
Just drop out the dropout.
okay.
Basically, there is research being done. Like the founder of CNNs himself says that like things like dropout shouldn't really like pooling. Like, why does it really work? You are throwing away information. Like, you can argue that, but like dropout is basically shooting to your network, and it works because it just has so much power, so much more computational power that would be needed minimally to achieve the same task. But like instead of dropout, there is now even some experimental research on this, that it's better to use just heavier normalization, do batch normalization, weight decay, and stuff like that, instead of dropout. And yeah, like slowly start dropping the dropout and go to different methods and read the research.
Yep, like there is a recent paper which mentioned about to not use dropout. And also it makes sense because you're destroying your architecture of your neural networks using the dropout. So it's better to cope up with, as Ron mentioned, normalization with more data. These are better techniques.
Okay, so drop out the dropout. Okay, 2 more questions. Is there a way to measure how similar data sets are?
Yeah, train them, train one, use it as a pre-trained model for the other one. If it works well, they are similar. If it doesn't, they are not.
Simple.
And it's just the domain knowledge. I mean, as simple as that. You know what kind of images are already contained in the large image data set, and what is your task. You just map it simply. I mean, simple way.
Great. Last question. Could we filter images when the name matches to other things like hot dog is name of a song, in addition to texture filter? Did you understand that?
Okay, could we filter images?
When the name of the file matches to other things like hot dog happens to be the name of a song.
Like how we load the data in this example is just, it gets the full path of the image and then regexes it to find a match. That's like, if you put a hot dog singer into the data set of images and he's in a folder hot dog, or he is named hot dog, then well, he will be classified as a hot dog.
Okay.
All right.
All right. Just one last thing from my side. I mean, could you guys tell us a little bit more about Scalable? You know, what are you guys really good at? What are you guys planning on for the next year?
Well, I think we can talk about like specifically to our AI team. So we are in total 8 people, and we have from a very different background. So for example, myself has a strong background in computer vision, while Ron comes with machine learning and mathematics. And our team is led by Charles, who has a PhD in physics from CERN. So we are like a lot of mathematicians there. So we don't only cover deep learning, we also cover the mathematical aspect of the AI, which is, personally, we believe is much more important to really understand the things. And as is Scalable, we are an IT software company, and we have, as I mentioned, we have nearly all the components which is required for developing a solid software, from back-end to front-end, to web developers, to mobile developer, and we are there as an AI team. And in addition, we also have UI, UX, so for the design purposes. Yeah, so if you want to develop any software, please feel free to come like from AI or non-AI side.
Perfect. Thank you, Ronald and Sanchit. Thank you very much. Please give them a big round of applause. And if you have any more questions for Ronald and Sanchit, please.